Welcome to the Deep Dive. We're the show that takes complex topics and, well, makes them make sense so you can get informed fast. Today, we're digging into something absolutely fundamental to AI, pattern recognition. You know how we humans just spot patterns, like seeing the signs of a storm coming, or maybe getting that weird feeling about a scam call, or even just noticing a friend's mood shift. We just do it. But imagine machines doing that, not just like us, but way beyond, on a massive scale, processing like unbelievable amounts of data in seconds. That's the huge shift we're talking about. AI can now sift through petabytes, that's millions of gigabytes, to find that needle in the digital haystack. It's the core skill that lets AI do so much, from telling objects apart to making predictions, and it's really changing everything.
It really is. And our mission today in this deep dive is to actually pull apart how AI learned to see these patterns. We're going to break down the basic steps, look at how powerful it is, especially for things like protecting you from online scams and fraud. And then we'll broaden out, see how it applies across, well, human behavior, nature, all sorts of systems.
Yeah.
And finally, touch on the really big questions it raises for society.
Yeah, and getting a handle on these mechanics is so important for understanding how AI is shaping your world, whether it's safeguarding your bank account or just picking your next movie. So let's get into it. How do the AI's eyes actually work? Okay, so AI doesn't have intuition like we do. How does it actually see a pattern then? It's not like it just knows, right?
No, definitely not magic.
Yeah.
It doesn't understand in the human sense. What it does is translate our messy reality into numbers, a massive amount of numbers.
Yeah.
It uses a mathematical language, the core idea. It breaks down data into measurable pieces. We call them features. And then its real strength is finding the consistent links, the statistical regularities within those features. It's a very methodical, mathematical way of looking at the world.
Okay, features. So data is the starting point. How does it get that data ready? It can't just use raw stuff, can it?
Right. The foundation is always good data. High quality, lots of it. Diverse data. Could be structured stuff from databases, text, images, audio, real-time feeds. And the quality, the variety, the sheer amount that directly impacts how well the AI performs. Garbage in, garbage out, basically.
Yeah.
So first, it needs cleaning, pre-processing, filtering out noise, irrelevant bits. Sometimes we even use data augmentation, creating more data artificially to make the AI stronger.
Okay, and then comes the feature extraction part you mentioned. This sounds like the really crucial translation step, turning raw data into something the AI can actually crunch.
Exactly. It's maybe the most crucial step. Feature extraction means taking all that raw, often high-dimensional data and boiling it down to the most important characteristics. Think of it like simplifying, getting rid of the noise and keeping the signal. We end up with these numerical summaries called feature vectors. It's dimensionality reduction, essentially, finding the variables that actually predict something.
Can you give us some examples? Like, what would features be for, say, an image versus text?
Sure. For images, it could be low-level things like pixel colors, how edges are oriented, different textures, color gradients, or more complex stuff like geometric shapes identified within the image. For text, features might be simple word counts, bag of words, or maybe TF-IDF, which measures how important a word is to a document, or even word embeddings, which capture like the semantic meaning and relationships between words. Audio, things like pitch, rhythm, tempo, tactical stuff like MFCCs. For financial transactions, it's often things like the amount, how often you transact, where you are geographically, the time of day.
Right, so the AI isn't seeing a face, it's seeing numbers representing distance between eyes, nose shape, etc. And the human choosing those features, that seems like it has huge implications.
Oh, it's absolutely pivotal. It's an act of translation, and it literally defines the AI's world. If you don't tell the AI to look for a certain feature, it's completely invisible to it.
Yeah.
The human choice of what features matter fundamentally limits or circumscribes the AI's understanding, and that's a major way bias creeps in, by the way.
Okay, so once we have these features, how does the AI actually learn the patterns? What are the main teaching methods?
There are a few main ways, or paradigms. The most common is probably supervised learning. Think of it like giving the AI a giant answer key. It sees tons of examples where the right answer is already known, emails labeled spam or not spam, transactions labeled fraud or legit. By seeing millions of these input-output pairs, it gets really good at recognizing known patterns. It's great for classification and prediction when you know what you're looking for. Precision based on past examples.
But what if you don't have labels, or you're looking for something totally new, something unexpected?
Exactly. That's where unsupervised learning shines. It works with unlabeled data. You just give the AI the data and say, find something interesting. Two main types here. Clustering, where it groups similar data points together, maybe finding customer segments you didn't know existed,
Mhm.
and anomaly detection. This is where it identifies things that just don't fit the norm, the outliers.
Yeah.
Crucial for finding brand new fraud tactics, the zero-day stuff that a supervised model trained only on the past would miss entirely.
Right, because it just flags something as different.
Precisely.
Yeah.
Different is suspicious.
Interesting. And there's a third way too, right? Reinforcement learning. Sounds more active.
It is. Reinforcement learning is more like how we learn trial and error. You have an AI agent interacting with an environment. It tries things, gets rewards for good actions, penalties for bad ones. Its goal is to figure out the strategy that maximizes its total reward over time. Think of training an AI to play chess or Go. In fraud, you could use it to simulate fraudsters trying different tactics, letting the defense system learn and adapt its strategies in real time. Very dynamic.
So for something complex like scam detection, you probably wouldn't rely on just one method. There's a trade-off.
Definitely a trade-off. Supervised models are accurate for known threats, but totally blind to new ones. Fraudsters adapt, right? Unsupervised models catch novelty, but they might flag legitimate but unusual behavior, like your first big international purchase, as suspicious. That causes friction.
False positives, yeah.
Exactly. So the best systems usually use a hybrid approach, multi-layered. Supervised for the common stuff, unsupervised as sentinels for the unknown, maybe reinforcement learning to keep adapting. It's a constant balancing act.
Okay, so those are the learning strategies. What about the actual algorithms inside? The brain's doing the processing.
Right, the architectures. The big ones everyone talks about are neural networks and deep learning. These are inspired by the brain interconnected nodes or neurons in layers. Data goes in, gets processed layer by layer with calculations at each neuron. Then, crucially, there's backpropagation. If the network makes a mistake, the error signal travels backward, adjusting the connections, the weights between neurons. It's like learning from mistakes, mathematically. And deep learning just means lots of these layers, which lets the network learn really complex hierarchical features automatically, like learning edges first, then shapes, then objects.
And are there specialized neural nets for different data types, like images versus text?
Oh, yes. For images, the champs are convolutional neural networks, CNNs. They use these things called filters that slide across the image, picking out features hierarchically, lines, textures, shapes, objects. It's how image recognition works so well now. For sequences like time series data or language you use recurrent neural networks, RNNs, they have loops, giving them a kind of memory. They can consider past information to understand context. That's key for things like stock prediction or understanding a conversation.
I've also heard about decision trees and random forests. Are they related or totally different?
Different approach, generally more transparent. A decision tree works like a flowchart of if-then-else rules. You can actually follow the logic, which is a big plus for interpretability. But single trees can sometimes learn the training data too perfectly and not generalize well. Random forests fix that by building lots of trees, like a committee, and combining their predictions. Much more robust. And another important one, especially for classification, is support vector machines, SVMs. They try to find the absolute best dividing line, or hyperplane, to separate different categories of data with the widest possible margin. Really good at clear-cut separation tasks.
And for unsupervised learning, you mentioned clustering. That often uses k-means.
That's a classic, yes. K-means tries to partition data into a specific number, K, of clusters. It iteratively assigns points to the nearest cluster center, then recalculates the center until things stabilize. Common way to find natural groupings. But here's a really interesting tension. The trade-off between how powerful these models are, especially deep learning, and how easy they are to understand. Deep neural networks are often called black boxes because their internal logic is incredibly complex and opaque to us. Why did it make that specific decision? Hard to say.
Right, which makes it hard to trust or debug or ensure fairness.
Exactly, and that's the whole motivation behind explainable AI, or XAI.
So XAI tries to crack open that black box.
That's the goal. XAI is a set of techniques to make these models more understandable. It can give you local explanations why this specific loan application was denied, maybe highlighting high debt ratio and short credit history. Or global explanations, like ranking which features the model weighs most heavily overall. For neural nets, there are ways to try and trace the decision path. It's absolutely vital for building trust, for oversight, for responsible AI.
Okay, this is making sense. Now let's apply all this to something really practical. Fighting scams and fraud. How does AI take the idea of deception and turn it into data patterns it can spot?
Well, think about it. Almost everything you do online leaves a digital trace. A login, a purchase, sending an email, even just how you move your mouse. AI fraud detection systems are designed to constantly analyze these trails, looking for the subtle signatures of malicious activity. Different scams leave different footprints, so you need different detection methods.
Like credit card fraud, that seems like a classic example.
It is. Credit card fraud often shows up as anomalies in transactions. Maybe a sudden burst of spending, or purchases from weird places or types of merchants you never use, or just spending patterns way outside your norm. Anomaly detection and supervised models are good at catching these.
What about account takeover, when someone gets into your actual online account?
That's more about access and control patterns. Red flags might be logins from a new device or location, especially followed quickly by a password reset and maybe a money transfer, or even just navigating the site in a way that's totally unlike the real user. That's where behavioral analytics and unsupervised anomaly detection really shine, and behavioral biometrics using deep learning.
And phishing emails, we still get so many. How does AI tackle those?
For spear phishing, especially, it looks for linguistic and contextual clues. Things like spoofed email addresses, language that creates urgency or fear, accounts suspended, urgent action required, suspicious links, maybe even tiny grammatical errors that sophisticated scammers now avoid. But AI can still sometimes pick up patterns. Techniques like natural language processing, NLP, sentiment analysis, checking links, identifying named entities, those are key.
What about really complex stuff like synthetic identity fraud, where they mix real and fake info? Sounds tough.
It is subtle. You're looking for weird relational patterns, maybe a credit file that looks too new or thin, combinations of personal details that don't quite make sense geographically or logically, or links between this new identity and known fraudulent accounts. Here, things like graph neural networks are powerful because they analyze connections. Unsupervised clustering and network analysis help map out these potentially fraudulent relationships.
It really sounds like anomaly detection is the bedrock here, spotting the odd one out. How does it establish what's normal to begin with?
It's absolutely fundamental, especially for catching new threats. It works by building a detailed dynamic profile of what normal looks like for a specific user or an account or even system traffic. This is mostly unsupervised. By having a really solid model of normal, anything that deviates significantly immediately stands out as an anomaly, needing investigation.
And it's not just looking for one big weird thing, right? There are different kinds of anomalies.
Exactly. There are point anomalies, a single data point that's way off, like that huge transaction on a normally low-spending card. There are contextual anomalies, things that are only weird in context. Logging in at 3 a.m. from a foreign country might be weird for you, but maybe not for someone who travels constantly. Context matters. And collective anomalies, a bunch of events that look normal individually, but together they form a suspicious pattern, like lots of tiny failed login attempts from different places all at once, signaling an attack. And instead of just saying fraud or not fraud, these symptoms usually produce a risk score.
So it's not just yes or no. That allows for a more measured response.
Precisely. Low risk, let it go through. Medium risk, maybe has for an extra authentication step like a code sent to your phone. High risk, block it automatically and alert someone. It balances security with user experience.
Okay, moving beyond just the transaction data, you mentioned behavioral analytics. Looking at how someone interacts, that sounds fascinatingly subtle.
It is. This moves beyond what you do to how you do it. The idea is everyone has a unique digital signature in the way they interact with devices. It's incredibly hard for a fraudster to fake perfectly. Deep learning models can monitor thousands of these tiny parameters constantly.
Like what kinds of parameters? Things we wouldn't even notice ourselves.
Absolutely. Your typing rhythm speed, pauses, how hard you hit the keys, how you move your mouse, the speed, the curves, the hesitations, even how you hold your phone, the angle, the pressure you use on the screen, your common gestures, plus your navigation habits, the order you visit pages, how long you stay, how you scroll. This is super powerful against account takeover. Even if they have your password, they probably don't type like you or move the mouse like you. It can even potentially detect if a legitimate user is being coerced by a scammer by picking up unusual hesitations or corrections.
Wow. And for scams based on language, like phishing, you mentioned NLP. How has that evolved beyond just spotting keywords?
Oh, massively. Early spam filters were pretty basic, just looking for words like Viagra or free money. Modern NLP understands context, intent, sentiment. It can really analyze the meaning and nuance of the text.
What are some specific NLP techniques used to spot these language lies?
Well, sentiment analysis looks at the emotional tone. Does it use fear, urgency, greed? Scammers love those.
Mm-hmm.
Named entity recognition, NER, identifies things like company names, locations, people. It can spot subtle impersonation attempts like PayPal with a capital I instead of PayPal with an L. Relationship extraction looks at the grammar. Does the email claim to be from Microsoft but is signed Amazon support? That's inconsistent. And topic modeling can compare the overall semantic fingerprint of an email to known phishing campaigns. Often these systems work right at the email server, blocking threats before you even see them.
Okay, but this brings up a huge, very current issue, generative AI. What happens when the scammers get tools that are just as good or even better than the defenses? It feels like a double-edged sword.
It absolutely is. Generative AI, especially large language models, dramatically lowers the skill needed to create very convincing scams. Malicious tools can now write perfect, persuasive phishing emails tailored to the victim, wiping out tells like bad grammar. They can automate creating fake profiles, scrape public info for social engineering, even generate deepfake voice or video for phishing scams or fake emergencies.
That's terrifying. But can't the same AI be used for defense, too?
Yes, that's the other edge of the sword. AI models are being trained specifically to detect AI-generated text or images that might be part of a scam. Generative AI can also create highly realistic synthetic data of rare fraud types. This is incredibly useful for training detection models, making them better at catching things they haven't seen much in the wild. Plus, AI assistants can help human analysts by summarizing case data, spotting connections they might miss. It speeds up their work.
So it really is this escalating arms race, AI versus AI.
That's exactly what it is, an accelerating adversarial game. And it probably means that in the future, trust might shift away from just the content of a message towards verifying the consistency of that message with the sender's known authenticated digital behavior. Your AI checking if that urgent request really sounds like something your boss would send based on past interactions.
What's really striking is how these core ideas, finding patterns, anomalies, behavioral signatures, aren't just for scams. They apply everywhere. It's like AI's universal toolkit.
Exactly. The same fundamental approaches that spot fraud can spot disease markers in medical scans, predict consumer trends, forecast weather, analyze ecological data. It's the generality that makes it so powerful.
So taking it beyond finance, how is it used to understand human behavior itself? Psychology, society?
It's giving us new windows into behavior. NLP analyzing language use, for instance, can pick up subtle linguistic shifts that correlate with things like depression or anxiety. Behavioral AI can predict and respond to actions. And interestingly, studies show people sometimes act differently, maybe more analytically, if they know an AI is observing them.
And companies use it all the time to figure out what we'll buy, right?
Oh, constantly. Think Netflix recommendations, Amazon suggestions, targeted ads. Companies process vast amounts of your interaction, data browsing, purchasing, viewing to spot patterns. They use this for audience segmentation, predicting trends, and delivering those highly personalized marketing messages and recommendations that sometimes feel uncannily accurate.
What about in education? How's AI changing learning?
This is a really promising area. Personalized learning is a big one. AI can analyze how a student interacts with online material, their scores, how long they spend, the kinds of mistakes they make. Based on those patterns, it can identify their learning style, find gaps in their knowledge, and tailor the educational path just for them. That's educational data mining. AI can also analyze things like attendance, platform usage, and assignment completion to predict which students might be at risk of falling behind, allowing for early intervention, though we have to be careful about potential bias in that data.
And in biology and health, with all the complex data there, AI must be crucial.
Absolutely. The sheer scale of biological data is perfect for AI. Genomic pattern recognition is huge, analyzing massive data sets to find complex gene patterns linked to diseases like cancer or Alzheimer's. That's the foundation for precision medicine treatments tailored to your specific genetic profile. Computer vision is also used to analyze movement from video, maybe spotting unusual crowd behavior for security, or analyzing someone's gait in healthcare to track recovery from injury, or diagnose neurological conditions.
Okay, shifting gears to politics and governance. This feels like a sensitive area for pattern recognition.
It definitely is, and it's being used extensively. AI analyzes social media, news, and other sources in real time to gauge public sentiment on issues or candidates. Machine learning models integrate polling data, demographics, economic indicators, online trends to try and predict election outcomes with varying degrees of success, of course. A huge challenge is misinformation. NLP helps track fake news, identify bot networks spreading it, and cross-reference sources. But again, it's an arms race because AI can also generate fake news. Researchers also use NLP on political text speeches, manifestos to track ideological shifts or see which issues gain or lose prominence. And just to be clear, we're reporting on these uses based on our sources, not endorsing any specific political applications.
Makes sense. And economics and finance fields built on finding patterns, how is AI turbocharging them?
Traditional economic models often struggle with the complexity and sheer volume of modern data. AI can process incredibly diverse datasets, news sentiment, satellite images of shipping activity, social media trends, things traditional models might miss, to forecast macroeconomic indicators like GDP or inflation more accurately. In financial markets, those RNNs we mentioned with their memory are used to analyze price history, trading volumes, market sentiment to predict short-term fluctuations for algorithmic trading strategies. And supply chains incredibly complex systems. AI finds patterns in sales data, market trends, even weather forecasts to predict demand, optimize inventory levels, and plan the most efficient logistics routes.
Lastly, let's look at the environment and climate. How is AI helping us understand and protect the natural world?
It's becoming indispensable. Deep learning models now produce incredibly accurate short-term weather forecasts globally, especially for extreme events, much faster than traditional methods. Agencies like NASA use AI to analyze long-term climate data patterns. Computer vision applied to satellite imagery is huge for monitoring deforestation, tracking illegal logging or agricultural expansion, even verifying reforestation efforts. For wildlife conservation, AI automates the tedious process of identifying animals in millions of camera trap images, analyzes audio recordings to monitor biodiversity, or tracks migration patterns from GPS data. It can even integrate data on vegetation health, water quality, and other factors to assess the overall health and resilience of entire ecosystems.
That's an amazing range of applications, but there's a flip side, right? The environmental cost of running all this powerful AI.
Yes, that's a critical paradox we have to acknowledge. Training these huge AI models, especially deep learning ones, requires massive data centers. And those data centers consume enormous amounts of electricity and often water for cooling, contributing significantly to carbon emissions. So while AI helps environmental science, it also has its own environmental footprint that needs serious attention and mitigation. But if you step back and look at the big picture, you see this unifying principle. Pattern recognition is like AI's core capability, its universal grammar. The same basic techniques work across all these different fields. That's its power generalizability. The limitation, though, is that it finds correlations, statistical links, but it doesn't truly understand the underlying causes or context like a human expert does. That's why human oversight and interpretation remain absolutely essential.
Which brings us right to the human side of things. Ethics, control, bias. The future. If AI is finding patterns in everything, including us, what does that mean? Let's talk bias first. How does it creep in?
Right. Algorithmic bias isn't usually intentional malice. It's more like a mathematical reflection and often amplification of the biases already present in the data we train AI on. If historical data reflects societal biases, gender bias in hiring, racial bias in loan approvals or policing, the AI will learn those patterns as normal and replicate or even worsen them.
Can you give some examples?
Sure, there are some well-known ones. Amazon had an experimental recruiting tool that learned to penalize resumes containing words like women's because its training data came from a historically male-dominated tech workforce. The COMPASS algorithm used in the U.S. justice system was found to be nearly twice as likely to incorrectly flag black defendants as high risk for reoffending compared to white defendants. A healthcare algorithm was found to allocate fewer resources to black patients because it used past healthcare spending as a proxy for need, overlooking systemic inequities in access and spending. Even generative AI can reproduce stereotypes. Ask for an image of a CEO, you might get mostly white men. Ask for a nurse, maybe mostly women of color.
So the AI is basically holding up a mirror to our own societal biases, maybe even magnifying them.
Exactly. It reflects the latent biases embedded in our history, as captured by data. Debiasing AI isn't just a technical fix. It's a deep ethical and societal challenge about the data we use and the values we embed.
And this ties back to the black box problem and the need for explainable AI, XAI. If we can't see why an AI makes a biased decision, it's much harder to fix.
Precisely. Opacity makes it difficult to trust the system, hard to debug failures, and easy to conceal discriminatory factors, intentionally or not. Accountability becomes nearly impossible. XAI's role here is crucial. By providing explanations, even partial ones, for how a model works or why it made a specific prediction, it helps us identify and potentially mitigate these biases. Those local explanations, feature importance scores, tracing decision paths, they all contribute to transparency.
When AI gets embedded in things like policing or deciding social benefits, you mentioned the term algocracy. What are the implications there, especially for things like free will?
Yeah, when algorithms start making or heavily influencing state decisions, governance itself changes. The rise of predictive analytics definitely creates this tension with our ideas of free will and agency.
Mm.
If an algorithm can predict your likelihood of doing something, defaulting on a loan, committing a crime, developing a disease, does that prediction start to feel like destiny? There's a risk of algorithmic determinism, where people are treated based on what a model predicts they might do, not what they've actually done. This also raises huge predictive privacy concerns.
That's profound. How might this impact us on a more personal level? Our behavior, our sense of self?
It could change behavior in subtle ways. People might consciously or unconsciously tweak how they act online or offline to try and present a favorable pattern to algorithms they know are watching, gaming the system. Recommendation engines, while useful, can trap us in filter bubbles or echo chambers, narrowing our exposure to different ideas and potentially reinforcing existing beliefs. On a perhaps more positive note, some argue that having AI as this distinct, non-human intelligence might actually strengthen our sense of shared human identity, the human in-group, against the machine out-group. And underlying all this is that persistent philosophical question. Could AI ever truly think or be conscious? Or is it destined to be purely computational intelligence? The jury is definitely still out on that one.
So faced with all this complexity, the power, the bias, the philosophical questions, what are the practical steps? How do we move forward responsibly?
It really requires a combination of approaches: technology, policy, and ethics working together. First, technology itself can help. Privacy-enhancing technologies, or PETs, aim to get the benefits of data analysis while minimizing privacy risks. Things like homomorphic encryption let you compute directly on encrypted data, so the raw data is never exposed. Federated learning trains models on data stored locally on devices like your phone, only sending aggregated updates back, not your personal data. Differential privacy adds statistical noise to datasets to mask individual identities while still allowing analysis of overall trends.
And on the policy and regulation front?
That's essential for setting boundaries and ensuring accountability. We're seeing frameworks emerge globally. The EU AI Act is a major example, taking a risk-based approach. Stricter rules for high-risk AI applications, like in healthcare or critical infrastructure, and banning certain unacceptable uses. The U.S. tends to have a more sectoral approach, with existing regulators adapting rules for AI within their domains. The key is creating legal structures for safety, fairness, and redress when things go wrong. But laws aren't enough. Organizations need strong internal ethical principles and governance, commitments to fairness, transparency, accountability, reliability, safety, privacy, security. That requires educating developers, robust review processes, and a culture of responsibility.
So wrapping this up, what's the final thought? What's the ultimate goal here?
I think the most constructive way to think about AI pattern recognition, ultimately, is augmentation, not automation. AI is phenomenal at finding statistical correlations in data at superhuman scale. But humans bring the context, the causal reasoning, the ethical judgment, the common sense, the creativity things machines currently lack. An AI might flag a pattern in a medical image. It takes a human doctor to interpret that pattern in light of the patient's full history and make a diagnosis. An AI flags a suspicious transaction. It takes a human analyst to investigate the nuances and decide on the right action. The future isn't just about building smarter machines. It's about figuring out how humans and machines can work together effectively and ethically. It comes down to human choices. We need to demand transparency, protect human dignity, ensure accountability, and always insist on meaningful human oversight. The goal should be to use this powerful algorithmic eye to broaden our own vision, to protect us, empower us, enlighten us, not to limit or control us.
This is DigitView.